So in this class, we're gonna see the definitions of convex and concave. So actually, formally, convex function can be defined as follows, but you can understand what is the convex based on this example. So here, suppose that our given function is convex. This one is convex. Then we can pick any kinds of two points on top of this curve. For example, A and D, and then we'll make a linear line which can pass A and D at first, and then every single point on top of this pass should be larger than equal to this function. And then we are saying that this function is convex. Okay, so for example, suppose that we are pick the other two random point, this one and this one, for example, and then we will make a line just like that, and any points on top of this line should be equals to or larger than the given function f of x. Okay, then that can be denoted by this one. Okay, so this is called convex. So we have another definition that is called concave. So in this concave function, we can think about the opposite. For example, suppose that our given function is concave, and suppose that we want to pick two random points on top of the curve, and then we'll make a linear line which can go through these 2 points, and then we have to say that every single point on top of this curve should be less than equals to this given function. And then in that case, we are saying that this function is concave. Okay, so this can be mathematically denoted by this one. Okay, so last time I told you that we have linear programming. In the linear programming, our objective function and constraints are all linear. Okay, and then if we have some non-convex terms in this optimization framework, then we are saying that that is nonlinear programming. Okay, in nonlinear programming, if our given function is convex or concave, then we can say that this can be solvable, which means that we can get the optimal solutions based on this formulation. But this is not, if this is not convex, then in that case we cannot get the optimal solution in a given time. That's why those are all NP-hard problems. So in this case, we have to use heuristics. But heuristics cannot guarantee the optimal solutions. That's why, if possible, we have to think about the convex only. So that's why when we have these kinds of nonlinear function at first, we have to determine whether the given function is convex or concave at first. If we can prove that this is convex, then it's good to go. We can get the optimal solution in a given time. Otherwise, we have to think about to use the other heuristics such as genetic algorithm, simulated learning, type search, and so forth. That's why checking the convexity is very important in this case. So in this lecture, we're gonna see about that. And then we have very quick theorems about that. Suppose that we have two convex functions, and the summation of the convex function or the summation of two concave functions are all convex and concave. This is trivial. And linear function can be convex as well as concave. Okay, so we have to think about this one. Okay, so in addition to that, suppose that we have these kinds of convex function, we have these kinds of concave function. So in a convex function, this is our minimum. This, in the concave function, this is our maximum. Suppose that we have the other type of the function just like that. So in that case, you can find some minimum values here and here and here, and then among these given minimums, the most minimum one is called global minimum, and the others are called, including this one, we are saying that those are all local minimum. Then on the other hand, when you pick the maximum one, just like that, and then among these given, these are all local maximum. However, we have to take the most highest one. Then in that case, that is called a global maximum. Okay, but in this case, convex or concave. So in convex, when you take our local minimum, then the local minimum should be global minimum because we have only one minimum value. So in the concave, when you take the maximum one, you can see that we have only one local maximum. That's why this is also called a global minimum. That's why this can be our optimal solution. Okay, so that's why convex and concave are guaranteed optimal solution in a given time, because we can compute the values in a faster manner. And this is very important. So in this case, this is our function. Okay, and in this function, we can segment our curve. This is A, this is B, this is C, and this is D. Okay, So then this is f. So we are going to take the first order derivation of this given function. Then it means that we want to check the angle. So angle is increasing, that's why this is plus. Angle is decreasing, this is minus. C is minus as well. D is plus. Okay. And when you take the second order derivation for the given function, then in this case our increasing ratio is decreasing. That's why this is minus. This is also minus because this is also decreasing a lot. And in this case, even though the tendency is decreasing, even though this is decreasing, but decreasing tendency is up rising. That's why in this case this is plus. In this case this is up rising a lot. That's why this is also plus. For example, in this case this can be this equation. For example, when you take the second order derivation, it becomes 2x and then again 2. So this is always 2. It means that they are positive, just like that. Then we can check that in the given here they are all negative. In this case they are all positive. And in this case this is our convex. This is our concave. This is our convex. Okay, so this is our concave. This is our convex. So we can say that in convex function, in the second order derivative results are equals to or larger than, is larger than 0. In this case, in the concave, the second order derivation of the given function is less than equals to 0. That's why we hold this property. So this is very important. That's why when you have given function, we always try to take the second order derivation. Okay, but in this case, in this example, we just have only one variable. So this is f, this is f. Okay, then suppose that we have n number of variables. Then we have to take the second order derivation for individual variables. That's why we need Hessian matrix, what we studied in the first lecture. Okay, that's why we need Hessian. Okay, in order to take the second order derivation for a given function in various variables. So here we need to think about the Hessian. Suppose that we have n different number of variables. That's why this one has very high dimensional surface or features in this case. And then in every single time we have to take the second order derivation. For example, this is our function x, y, g. And then we have something like the function. We have the function with 3 variables. Then we have to take the Hessian just like that. The Hessian is we have to take the derivation with the x 2 times, x and y, x and g, y and x, y and y, y and g, g and x, g and y, and g and g. Okay, so then this is our Hessian matrix. So in this case, in previous case, we did 2 second order derivation for a single variable. So in the case we can check that this is negative, this is positive. Okay, and then in order to conduct second order derivation with multivariate functions, and then we have to think about all kinds of combinations. That's why we have these number of different results. Okay, that's why we need to take the Hessian at first, and then we have to see the property of this given Hessian function. That's what we have to do from now on. So suppose that we have n-dimensional function just like that, and then we have to determine whether the given function is convex or concave. So in that case, we cannot draw a figure because n dimension is very high. That's why we cannot see this one visually. That's why we cannot use the graphical solutions. We have to use mathematical solutions for this purpose. That's why we need to understand what is the second order Hessian. So this is one example about that. We have 2 variables, x of 1 and x of 2. So in this case, we want to do the derivation with x of 1. Then it becomes 3x1 to the 2 plus 2x2. In this case, we want to take the second order derivation, x2. That this is ignored, 2x sub 1 plus 2x2, okay? And then we are taking the derivation with s sub 1. This becomes 6x sub 1. And when you take the derivation with the x sub 2, it becomes 2. When you take the derivation with the x sub 1, it becomes 2. When you take the derivation with the x sub 2, it becomes 2. Okay, that's why it becomes 6 2. So it becomes 6 2 2 2. So this is the result of the Hessian. Okay. So now we have to think about the definition of a principal minor. Principal minor means means kinds of subset of these matrices determinant. Okay, determinant of any kind of subset matrix. For example, in this case, we want to calculate the first order of principal minor, and then we take the first element matrix from this one, and this one, because this is by 1 1, this is by 2 2, because I and I, they are same to each other. Okay, so that's why we have to take the determinant of this one. That's why this becomes -2, this becomes -4. So these are our first principal minor. Then when you want to take the second principal minor, then in the case we have to take the 2 1 2 1 2. When you take the 2 from here, we are taking the entire matrix. That's why we have -2 -1 -1 -4, and then in the case we have to take the determinant. So in the case we are doing this calculation, that's why this becomes 7. Okay, so then -2 -4 are our first principal minor, and then 7 is our second principal minor. Okay, so when you want to calculate the first principal minor, so in the case we are taking this component, and so forth. That's why these diagonal entries are our first two orders principal minors. That's why you don't need to calculate a lot. So from now on, we want to see what is the leading principal minus as well. So in this case, our leading principal, so this one, so when you take the first order principal minor, I told you that these are our first order principal minors, so A, E, F. So for the second principal minor, we have 2 1 2 3 1 2 3 1 2 3. So in that case, we have to take 1 2 1 2. So that's why it becomes AE minus BD. And then when you take the 1 3 1 3, then AI minus CG. So when you take this one and this one, then EI minus FH. These are our second order principal minor, first order principal minor for the last one. And then we are doing some more calculation. So we're gonna see what's that next time. But in that case, we want to take the leading principal minus. Then we are taking this one, and we are taking this one, and so forth. So we want to take the thing which take the highest position. Okay, that's called leading principal minor. So in the case, let's do the exercise with this one. So we are not do the derivation with this one at first with x1. This becomes 3x1 to the second plus 2x2, and in this case we want to do the derivation with the x sub 2. Then it becomes 2x1 plus 2x2, and then we are taking x sub 1 again. Then this becomes ux1, and we are doing the derivation with the x sub 2 again. It becomes 2. We are doing the derivation with the x sub 1, then it becomes 2. We are doing the derivation with the x sub 2, it becomes 2. Then the matrix becomes x sub 1 2 2 2. And then our first leading principal minor will be this one. That's why we only have this one. And in this case we have this notation. When we have h sub 2, this becomes h sub 2, right? So in the case we are doing the AD minus BC. That's why it becomes this one. Okay, that's why we have this result. Okay, now this is the most important slide, I think, in this lecture. So in this case, up to now we want to calculate a first principal minor, second principal minor, a third principal minor, and so forth in a given Hessian matrix. So when you calculate these principal minors, if all principal minors are non-negative, then in that case we are saying that this is convex. And in other case, the sign of the first principal minor are all negative. Second principal minor sign will be all positive. Third principal minor signs are all negative, and so forth. Then we are saying that this function is concave. Okay, we should remember this one. So in that case, even though we have a very high order function in this case, when we calculate the Hessian, second order Hessian, and then when we take the first, second, third, and so forth principal minors, and then by checking the signs of the values, we can confirm that the given function is convex or concave or nothing. Okay, so let's do more exercise about that. Okay, so now, so let's do the let's calculate the Hessian at first. We are doing the derivation with x of 1. It becomes 2x1 plus 2x2, and that's it. When you calculate the derivation with x of 2, it becomes 2x1 plus 2x2. When you take the derivation with x of 1, it becomes 2. When you take the derivation with the x of 2, it becomes 2. When you take the derivation with x of 1, it becomes 2. When you take the derivation with x of 2, it becomes 2. That's why the components are 2, 2, 2, 2, 2, 2, 2, 2, okay? And then we want to take the first principal minor. In that case, I told you that we have to take the diagonal entries. That's why 2 and 2. What is the second principal minor? In that case, we have to determine the determinant of this matrix. That's why it becomes 2, 2 minus 2, 2 becomes 0, right? So those are all non-negative. These are all non-negative. That's why we are saying that this is convex function, okay? So even though we have then, when we have a lot more dimensions in a given function, then we can easily confirm that this is convex or concave, even though we cannot see how it look like, okay? So let's look at another example. So in this case, we want to derivation with x of 1 at first, then it becomes 2 minus 2x1 minus x2. We want to take the another derivation with x of 1, it becomes minus 2. When you take the x of 2, it becomes minus 1. When we are doing the derivation with x of 2, it becomes minus x of 1 minus 4x of 2. And then we are doing the derivation with x of 1, it becomes minus 1. When we are doing the derivation with x of 2, it becomes minus 4. So this is minus 2, minus 1, minus 1, minus 4, okay? So then, let's calculate the first order principal minor, okay? Then I told you that we have to take the diagonal entries. That's why it becomes minus 2 and minus 4. Then what's the second order principal minor? So in that case, we have to take the AD minus BC. So minus 2, minus 4, minus 1, minus 1. It becomes 8 minus 1, becomes 7. So the signs are all minus, signs are all plus. That's why this is the, this result satisfies the conditions of concave. That's why we are saying that the function is concave, okay? Let's go to the other example, okay? So in this case, we have to take the second, we have to make the Hessian matrix at first. So we are doing the derivation with the x of 1 first, 2x1 minus 3x2. When you take the derivation with the x of 2, that's why it becomes minus 3x1 plus 4x2. And then we are doing the derivation with the x of 1 again, it becomes 2. We are doing the derivation with the x of 2, then it becomes minus 3. When we are taking the derivation by x of 1, it becomes minus 3. When you are taking the derivation of x of 2, it becomes 4. That's why it becomes 2 minus 3 minus 3, 4. So we have to take the first order principal minor. So in that case, we are taking the diagonal entries. That's why it becomes 2 and 4. When you want to calculate second order principal minor, it becomes 2, 4 minus 3 becomes minus 1. So this one is all positive. That's why if this function is convex, and this should be positive or non-negative, but this is negative. That's why this is not convex. But if you want this function be concave, then these should be all negative, but they are all positive. That's why this is not concave as well. That's why this is not convex as well as this is not concave, okay? So this is just nothing. This is just a non-convex, which cannot guarantee the optimal solution in a given time. So now let's go for more complicated one. So up to now we saw about the three-dimensional surface. So it becomes x and y, for example. So this is x, this is y, this is f. That's why this function is three-dimensional. However, here we have three variables inside the function f. So in that case, this is four-dimensional curve. Four-dimensional curve cannot be drawn by human visual system. That's why we cannot see how it look like. However, we have to determine whether the given function is convex or concave. So then in that case, we are using the Hessian, okay? So now, in order to calculate the Hessian of this one, we have to make the matrix just like that, x1, x1. We are doing the second order derivation with the x1, 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 x2, x1, x3, x2, x1, x2, 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 x3, x3, x1, x3, x2, x3, x3, okay? So let's do the a derivation with x sub 1 first, and then it becomes 2x1 plus minus x2 minus xc. Then when you want to do the derivation with x sub 1 again, it becomes 2. When you want to do the derivation with x2, then it becomes minus 1. When you want to do the derivation with x sub 3, it becomes minus 1. Okay, that's why this becomes 2 minus 1 and minus 1. And then let's go to the second one. Okay, so in the case, suppose that you want to do the derivation with x sub 2, then it becomes 2x2 plus minus x1 minus x3. And then when you want to do the derivation with x sub 1, it becomes minus 1. When you want to do the derivation with x sub 2, it becomes 2. When you want to do the derivation with x sub 3, it becomes minus 1. That's why it becomes 2 minus 1 minus 1. Okay. The last one, you want to do the calculation, derivation with x sub 3 at first. It becomes 4x3 minus x2 minus x1. And then when you want to do the derivation with x sub 1, it becomes minus 1. When you want to do the derivation with x sub 2, it becomes minus 1. When you want to do the derivation with x sub 3, it becomes 4. Minus 1, 4. Okay? So in this case, you want to calculate the first order principal minor first. That's why it becomes 2 to 4. 2 to 4, that's fine. So for the next, you want to calculate the second order principal minor. So in this case 1 2 3 1 2 3. Then you have to organize new matrix with given with 2 selected 2 among given 3. That's why you can take 1 and 2, then 1 and 2, 1 and 2, then this matrix 2 minus 1 minus 2. So you have to take the determinant of this one. Okay, becomes 4 minus 1 minus 1. So it becomes 3. Okay, so you take the 1 and 3, then you take the 1 and 3. That's why it becomes 2 minus 1 minus 1 4 and determinant. And then it can be 2 4 minus 1 minus 1. So it's 7. So now the last one, you have to take this one and this one, 2 and 3. So this is 2 and 3. So it becomes determinant 2 minus 1 minus 1 4. So it becomes 2 4 minus 1 becomes 7. That's why 377. Okay, as you can see here, 377. Okay, so you calculate the first order principal minus, second order principal minus. Now it's time to think about the third order principal minor. So you have to keep in mind that in third order, you have to take the determinant of this given entire Hessian matrix. So in that case, the determinant can be obtained as follows. You take this one at first, and then you take this one. Okay, so then you are doing 2 determinant 2 minus 1 4 and minus. Then you take this one and this one and this one. Okay, so minus 1 determinant minus 1 4 plus. You take this one and this one. Okay, plus minus 1 determinant minus 1 2 minus 1 minus 1. Okay, so then you also keep in mind that this sign is changing. Okay, and then this becomes 2 multiplication 7 minus 1 minus 4 minus 1 plus minus 1 1 minus 2. Okay, becomes 14 minus 5 minus 3 becomes 6. Okay, so this becomes 6. So here you can check that this is positive. This is also positive. This is also positive. So you can say that all principal minus of this Hessian are all negative, all non-negative. That's why this is convex. Okay, so this is how you can determine the given function is convex or convex. This is convex or not convex. Okay, so here you have to understand this one very correctly, and then you can use this one for many applications. So in while scheduling problems, you have to do the scheduling decision at first, and then you may want to do additional decision, how many data rates should be allocated on top of the scheduled link. So in that case, you are doing the nonlinear programming solution. So in that case, you can easily check that this is non-convex. That's why this is very well-known NPR problem. So we're gonna see how you can relax this non-convexity in a later time with one paper. So in addition to that, in addition to the paper reading, I posted the paper in the blackboard, and then I will give you some more examples in order to solve these kinds of convexity determinants. Okay. So before ending, I would like to give you some more interesting example. So let's check whether this function is convex or non-convex. So in that case, we have two variables, right? Then we can get the Hessian just like that, determinant by partial derivation by x2 times xy, yx, y, and y. So in that case, when you take the partial derivation with the x, it becomes y. When you take the another partial derivation with the x, then it becomes 0. When you take the partial derivation y, it becomes 1. When you take the derivation of this one by y, then it becomes x at first. And then when you take the derivation with the x, then it becomes 1. When you take the derivation with y, it becomes 0. Then the Hessian becomes 0, 1, 1, 0. And the first order principal minus are 0 and 0, that's fine. But second order principal minus are AD minus BC, determinant of this one. That's why this becomes 0 multiplication 0 minus 1 multiplication 1. That's why it becomes minus 1. That's why this is negative. So second order principal minus are all negative. That's why you cannot say that this is convex. So this is very well known non-convex problem as well. So later we will gonna have some more discussions about this one. Okay, thank you, and let me upload another video maybe this weekend or early of next week.